Hey guys, can you hear me well?
Hello, yes.
Okay. So we wait a bit. We are only 8. It's still like 3 minutes to 4. Okay, let's share my screen. Okay. This should be okay. So I also uploaded the material on the web. You have in the online materials folder, you have the PPTX and the PDF. And on Moodle, I only uploaded the PDF version. The one with PPTX is basically the material that I have now in my front, containing all the animations and maybe some comments from some for some slides. So let's wait another 2 more minutes and then we start. Okay. Okay, so can you see my screen with the first slide? Okay. Okay, I also have the chat open here. Maybe put here. Okay, so yeah, before I start, so today in the morning, I recorded another session for the seminar for the advanced machine learning. There was some problem on some problem from my side on Friday. I think I didn't press actually the button for recording the seminar session. Yeah, so I am recording this. Yeah, I I I check I I check this stuff. Let me check in. Let me check again. This is recording. Yeah, so actually it's 4 p.m. and this is recording. Okay. Yeah, so on Friday something has happened. I didn't press the recording button, so I only recorded the lecture. But today in the morning, I recorded again the seminar class for the advanced machine learning seminar number 2. I re-explained all the problems, and in fact, I added explanation for the problem 4 and 5. And now on the web you have more complete material. There are now 10 pages. I added like 3 pages proof for exercise 4 and 1 page proof for exercise 5. And the plan is that on Friday for advanced machine learning, we will meet for the lecture from 8 to 10. And from 10 to 12, the idea is to have a session for question and answering. I think given the fact that the seminar it's online and you have all my explanations and you have the solution posted on Moodle, it doesn't make sense for me to repeat again my explanation. So we can just meet on Friday from 10 a.m. and if you have some problems that you didn't understand, you can ask me, and I will try to give you some explanation such that nothing remains unclear. So now we come back to the computer vision lecture. It's lecture number 5. So before we start, we have an announcement. So Juliana told me to inform you that she will hold the computer vision lab classes tonight from 6 to 8, and also next week online. She is not using the Zoom platform. She's using the Google Meeting Hangouts. She made 2 groups. One group for the students that will join the lab class today in the week 7, week 9, and so on. And there is another group for the students that will come to the lab class on next week and week 8 and so on. So just enter on this group, and Juliana has prepared the material. In fact, we both prepared the material for the lab class. Tomorrow morning, I will teach the same lab. Hopefully, I can install OpenCV on my laptop and run the code here. Otherwise, I will run the code from my desktop and try to connect from my desktop. Okay, and before we start, we noticed that there is a problem with annotations for your project. We only discovered just one wrong annotation. So if you look at the particular image number 12, Juliana told me that there is something wrong with the annotation that we had, because in the meantime we changed it. So if you look on the left image, in image 12, you see that physics is selected and the variant is number 3, whereas in the annotation file you see F from physics, but it's number 2. However, if you go to the correct number of answered questions, it's 19 times 0.3, it's 5.70 plus 1 is 6.70. So the only problem is that here it's F2. In the meantime, so if you go again on Moodle and go to the folder with the materials, you will see that the annotation for image 12 has changed. Now, if you notice other mistakes from our side, just let us know, and we'll make sure that we will change. Okay. Okay, so let's recap a bit what we did last time. So last time, I think in the first hour, I explained the K&H detector. So you have an input image, and you want to detect edges, and this will be very useful for your project to detect the lines. Actually, the K&H will not provide you exactly the lines, but it will provide some low-level features such pixel on edges. These pixel on edges are called edges, and you can post-process and these edges and obtain lines. Okay, and we also started a bit, and we just covered just a small part of what is called texture. We ended, I think, with this slide. There are other great things that you can do with texture. For example, you can do what is called texture synthesis. You have a small image like this one, and this one, and you like to have an algorithm that basically identifies the statistical properties of your textiles, and for example can recreate a texture with whatever resolution you want, and also you can do what is called texture transfer. Given an image, you can do synthesis on your texture, but you can also superimpose over the content image, such that in the end you will obtain the original image having the texture of your having the style of your texture. And you can see here for the first image here and for the second image here, some of you could be familiar with this algorithm because in the past I teach this stuff, but at the master level we want to do more cool stuff, and we don't have so much time to do this part. Actually, this doesn't it's not so strong related to computer vision. It's basically related to computational photography, so we can skip it. There is no problem with this. And of course, there are many modern approaches that do texture transfer, and these modern approaches are called image style transfers. The idea is that you have a content image, and then you have a texture image, and what you want is to have an algorithm that will basically redraw your content image and will transfer the style from your texture image into your content image. So you can see here the same input image that is drawn 3 times, but each time is drawn with another style. And modern approaches that do this stuff, they appeared in 2016, and they usually rely on convolutional neural networks. This is a topic that we'll not cover in this lecture. Next year, in semester 3, in the first semester of your second year, Radu will teach about convolutional neural networks, and it might cover this part. So we're not going to cover too much about texture. We only stop here, and the plan for today is to cover this chunk, to go to the second module and to cover fitting curves and lines, robust fitting, ransack, and half transform, and let the color part for the next time, because I think it's a much better plan to do this stuff in just a single lecture. Otherwise, we would have covered the color part in the first part of our lecture, and then split this stuff in in two pieces. And I think if we just covered these two things, fitting and ransack, and also half transform is just one lecture, it's much better for you. And also it's better because you can use in your project the idea of using half transform to detect horizontal and vertical lines. Okay, so we start with fitting, and you can see from this image that this will help you basically to detect lines in your image, and for your project will be quite cool. And indeed, what we're gonna cover today is to detect lines, detect circles, and detect arbitrary shape in images based on some low level feature such as edges. So last time we learned how to detect edges by employing the can edge detector, and now we are at the point where we want to use these low level features to obtain a high level a representation. Maybe just move to lines, try to use the output of our Kenny edges of our Kenny edge detector to detect edges in an image. However, if you look to the to the right image, you can see that if you would only rely on the Kenny edge detector in order to detect lines, there are some huge problems. You have a lot of noise. Some parts of the lines are missing. So you want to employ some advanced methods such that you will discover lines in your image. So we'll talk today about fitting. Is just choosing a parametric model to represent a set of features, and we will look for methods for simple models like detecting lines or circles. And we will also see some modern stuff that was done in 2006 and that used half transform to detect cars in an image. And this is basically part of the modern computer vision stuff. So if you want to detect lines, there are a lot of problems if you only rely on a Kenny edge detector. So one problem is that you can have noise. You can have a pixel that maybe they are not discovered as edges, or maybe the binary edge map that you obtain as the one in the right image could give you edges at places such that your edges are misaligned, and the points from your line would not be very well aligned, would not be collinear. Another problem is that because of clutter, you have here textured areas. So if you look in the left part of the image, you have some tree here. If you employ your Kenny edge detector, you'd see that you'd have many edges here. So from this point of view, you'd have a lot of noise, and also you'd have some occlusions. You'll also have some missing data. So for example, if you want to detect these vertical lines or this vertical line for the building, you would see here that your Kenny edge detector will miss some edges on this line. So relying only on your detector, on your edge detector, is not such a good idea, and you like to employ some advanced methods to solve this problem. So we'll first look at some methods that you might be familiar with, and then we'll go to some specific methods that really work well in computer vision. So if we will know which points belong to a line, how we can find the optimal line parameters, one way is to go for the least square methods, and these methods should be very familiar with you. the other methods is to do some robust fitting if we have outliers, and a very nice method, it is called random sample consensus. It has acronym RANSAC, and we will use it a lot in the third part of our laboratory class when you want to match your test sheet for the project. If you have a picture taken in perspective, then you would employ a RANSAC method in order to obtain the geometric perspective transformation that would transform your test sheet to a template test sheet. We're gonna talk about this when we come to the lab number 3 to cover the project stuff. Okay, and we also talk today if there are many lines, how we can detect all the lines, and here we will also use RANSAC, and we also use what is called half transform. So let's start with a method that it is very easy and you should be familiar with it. Least squares line fitting. So our data consists of pixels that are part of our line. Basically, these are called edges. There are output of our K-edge detector, and the idea is that they could be very misaligned. They could be not very collinear to form a line. So you would like to find your line such that all these pixels are part of design. So basically, you like to fit a line such that you want to minimize a cost function, and the usual cost function is the errors from each pixel to your line is expressed here as the sum of square differences yy minus m xi minus b, where m is the slope of your line and b is the intercept of your line. So if you express this in terms of matrices, so you denote with y the vector, the matrix with one column and n lines, and that comprises numbers y1, y2, yn. With x, you have a matrices with 2 columns and n lines, x1, xn on the first column and only once on the second column. And b and capital B, it's a vector which it's a column vector containing what you want to find, the slope m and the intercept b. So if you use this notation, you can write it to be the squared norm of the matrix y minus x times b. And if you do the calculations, so you'd have that the squared norm is y minus xb transpose times y minus xb. And if you do the partial derivative to respect to m and to respect to b, this basically means that you obtain the partial, you compute the derivative of your cost function e with respect to the vector b, and you apply the math behind this stuff. So if you have b transpose another vector, if you take the derivative, you would obtain that vector, and so on. So if you apply this stuff, you obtain the solution written here. So you would obtain that b, the vector containing your slope and your intercept b equals with the inverse of the matrix x transpose x times x transpose y. Of course, that this solution exists if your matrix x transpose x will be invertible. Now, if you look very close to what I wrote here, you'll have a big problem when you want to fit a vertical line, because for the vertical line, your slope should be around infinite. It's either minus infinite or plus infinite. So this method definitely will not work for the vertical lines. So here you would have to do something else. So the problem of least square fitting is not a rotation invariant. It will not work for the vertical lines. So here we will do what is called total least squares. So instead of taking the errors between the points x, y, y, x, y, and y, and their projection and their ordinate for the on the line, you will just project these points on the line. So we will compute for each point. We will sum up the distance between the point x, y, y, and your line that is parameterized by the equation ax plus by minus d equals 0. And the vector AB, it will be the normal for the line, and AB is taken such that a squared plus b squared equals 1. So if you have this parametrization, then the distance between a point x, y, and the line given by the equation ax plus by minus d equals 0 will be, of course, given by the absolute value of axi plus byy minus d. Of course, that if you have the point x, y, on the line, then x, y, will fulfill the equation of the line. So you'll have that axi plus byy minus d equals 0. Yeah, so this is very intuitive because your point will be on the line. Now, if you come up with this parametrization, so now you want to find A, B, and D, such that you want to minimize. So you want to fit the line on your training data. You have some edge point x, y, y. So the problem that you want to solve, you want to find A, B, and D such that the cost function is minimized. So you want to minimize the sum of squares of the terms given by axi plus byy minus d. So you employ, you take the partial derivative with respect to A, B, and D. Computing the partial derivative with respect to D will lead you to the fact that D should be equals with A, and x overlined is basically the mean value of all the values xi, and y bold is basically y mean is the mean value of all your points y. And now if you replace D with what you have obtained, A and x mean plus B y mean, then you would have that E, your const function, can be written as the sum from y equals 1 to n. A times here you'd have xi minus x mean. This x mean comes from D plus B times y minus y mean, that also comes from D squared. And you can think of this sum as being the Euclidean norm of the vector, which has the first component being equal with ax1 minus x mean plus by y1 minus y mean. The second component, it's a times x2 minus x min plus b y2 minus y min, and so on. And this vector can be computed as the product between this matrix having n lines and 2 columns, and this column vector which has 2 lines and 1 column. So so this is the Euclidean squared norm of the vector. So it will be equal with un transpose times un, where again n is the vector ab, which has the property that a squared plus b squared equals 1, and u will be this matrix x1 minus x min, y1 minus y min, and so on. So if you now want to compute the partial derivative of your const function e with respect with a, n, and b, you can write this as the derivative of your const function with respect to the entire vector n equals ab. Now you follow the same derivation rules for vectors. So for example, if you derive this with respect to n, you would obtain, so un transpose derived with respect to n will be, so this is n transpose times u transpose. So you would obtain u transpose times u times n plus un transpose, and if you derive this, you would obtain here u. So in the end, the second term will be n transpose u transpose u, which will basically is the same stuff as the first term, because these are scalars. So in the end, you would obtain that this number, that the derivation with respect to n would be 2 times u transpose u times n, if this equals 0. So in order to find the solution n that fulfill this this requirement, then and also that the norm of the n vector equals 1. So your solution to this optimization problem will be that n is the eigenvector of u transpose u that is associated with the smallest eigenvalue, and this basically is the same stuff of coming up with a solution in the least square for the homogeneous linear system un equals 0. So you basically, so in this case, if you want to fit a line, you just have to compute the eigenvalues corresponding to the smallest. So you want to compute the eigenvector corresponding to the smallest eigenvalue of this matrix u transpose u. If you look very closely to this matrix, this is what is called in statistics the second second moment matrix, where you have x min is the mean of xy, and yy and y min here will be the mean of the yy values. So in the end, you will come up with your solution n, that is basically, it will define the normal to your to the line. And if you go back, then you'll find d, because d was defined based on your points and based on your a and b. So there is also another way to formulate the least squares problems. You can see the least square problems as the likelihood maximization in the following way. So you can see that these edge points that are not real aligned for your line, So you can see these points as being generated by the following process. You have UV, it's a point on the line, and then you sample a noise that has zero mean, and that has zero mean and standard deviation given by sigma, and you add to the UV point that it's on the line, you have this epsilon times the normal direction to your line AB, and you can see this each point XY is being generated by this process. And now the idea is that you want to come up with the parameters A, B, and D that will define your line AX plus BY equals D, and you can employ basically what is called maximum likelihood. You want to obtain parameters A, B, D that will maximize the product given by the likelihood function. So if you work out all the computations, in the end you will obtain the log likelihood function that is basically the cost function given by your least square problem. So this is another way of seeing how you can obtain your least square problems for fitting a line to the training set of points X, Y, Y, Y. Now, using least squares is a nice method when usually you have small differences, small misalignment from the points to the line. There is a problem with this method when you have some noise. So if the noise is very small, so in our case the noise is given basically by how far these points are far from your line. So if these distances are quite small, then the least square will work fine. The problem is that when you encounter some outliers, like in this example, so you can see here that if you apply the least square fitting, you would obtain a solution which is quite bad. So you would obtain a line that will minimize the cost function E, that the sum of square differences between each point and your line will be minimized. However, the type of solution that you would obtain in terms of quality, it's very bad. So in this case, you like to have some robust estimators, and the general approach here is to use a function which is called in this last row, which is a robust function which has some parameter sigma, and this sigma is called a scale parameter, and it has also an argument which is the residual of the ith point with respect to the modal parameter theta. And the idea here is that if you have an outlier, this RE of XC2 and theta will have a very huge value, but your robust estimator should minimize this value. And you have here an example of such a function. So if you consider this function rho of the two parameters u and sigma, so it's u square over sigma square plus u square. So you see for different values of sigma, so for example, sigma square equals 0, 1, or sigma square equals 1, or sigma square equals 10, your robust estimator would basically bound the value of any point that departs from 0 to at most 1. So this could be a possibility such that you'd have what is called robust fitting, and these kind of examples will be managed properly. Okay, so now robust fitting is a more complex problem. It's a non-linear optimization problem that here you have to solve it in many iterations, and least square solution can be only used for initialization, and of course it depends on the parameter sigma that you choose. If you choose here, so if you choose sigma just right, so sigma can be chosen such that you'd have so if you go back to your function here, so you like to choose sigma such that if you have small errors with respect to the line, this function rho should give you in the end a good estimate of your line, whereas for this point that is an outlier, your robust estimate will bound the distance that this point has to your line, and in the end you would obtain a very nice fit for your line, no matter the fact that you have this outlier point in your image. Now, if your sigma is too small, then you are in the case where you'd have a high error for all points that were very well aligned, and in this case you would obtain a line that basically fits very poor the data. And of course, if your parameter sigma is too large, you are back again in the case where you have basically a solution that is very similar to the solution provided by the least squares. Okay, so now ransack is a technique that was proposed in the 80s. Its acronym comes from the random sample consensus, and the idea basically here is that this is a very robust method that can deal with many outliers, and the basic idea behind this method is that at each time you like to choose a very small subset of points that were randomly sampled. Usually you take a subset that is equal with the number of points that will define your model. For example, if you want to fit a line, you will need two points. If you want to fit a circle, then you need three points, because a circle is defined by 3 points. If you like to fit a square is parameterized by 4 points. For a square, basically you need the center, 2 points. You need an orientation of your square, another parameter, and you also need a length of one side. So you'd have four parameters. If you want to fit a rectangle, you need 5 parameters because you have the center, 2 parameters. You have the orientation of your rectangle theta, it's another parameter, and you have the width and the height parameters of your site. So you choose a small subset of points in order to fit a model, and then you like then to find all the remaining points that are very close to the model and reject the rest as outliers, and then do this many times and see what kind, for example, what kind of models will fit your data very well. So we will exemplify this for fitting lines. For lines, we will only need, at each time we will only need to select just 2 points. So of course, if you try to do the least square fitting that takes into account all the points in the image, your solution will look very bad, like this one. This is the solution that basically will fit the line for which the total sum of square errors given by the distances between each point in the image and the red line, it's minimized, but of course it's not the solution that you are looking for in the image. So you would do the following steps. You would first select, for example, two points that will define a line, and then you will build your model based on these 2 points. We do know that a line is defined based on these 2 points. So you will build the line, and then you would compute the error function of each point in the image with respect to your hypothesis, to your build model. And this basically means that you will compute for each edge in the image. You will compute the distance between that point and your line. And then you will select points that are consistent with the model, meaning you would basically have a threshold, and you will count what are the number of points which are at distance at most that threshold. And then you would repeat this stuff for several times, and in the end, basically, you will keep some lines which will fulfill some criteria. So for the example here, you have a sample here. You choose the 2 red points, and if you see the 2 red points will lead to a line that will have a very large number of points that follow this line, and these points are what is called inliers. And here you'll have a solution that basically has very small number of inliers. So the algorithm ransack for line fitting, it's summarized here. So you would repeat for n times the following steps. You would draw S points uniformly at random. In the case of lines, S will be 2 because 2 points will define a line. Then you would fit the line to these 2 points. You would find inliers to this line among the remaining points. So all the points whose distance from the line is smaller than a threshold t. And if there are d or more number of points which are called inliers, you would accept this line, and you will refit using all the inliers that you have obtained. Okay, now how do you choose these parameters? So you have n, you have s, you have t, and you have d. S usually is typically choose as the minimum number needed to fit the model. So 2 for lines, 3 for circles, and so on. The distance threshold t. So usually you should choose t based such that the probability for an inlier it's p. So for example, if you consider that p equals 95%, then if you also if you consider the assumption that you have noise that will perturb your points, and this will make your points to depart with a distance that is given by a random variable that follows the Gaussian distribution with zero mean noise and sigma standard deviation, then in order to have like 95% of the points to be to follow, to be so in order to have 95% of the points to be inliers, and if you know sigma, then you should take t to be basically in the interval minus 1.9 plus 1.9 sigma. So you would choose t to be distance 1.9 sigma. And how many times you would repeat this process? So this capital N should be such that at least one random sample is not contaminated, so it's free from outliers. So if you assume, for example, that that p equals 0.9999 and the outlier ratio it's e, then you would end up with this number, which actually, if you look very closely, has to do something with what we are computing the probabilities for obtaining an error for the classifier at the advanced machine learning lecture. So here in the left part, so let's say that you want that with probability 99%, you want to obtain a model that is free of outliers. So basically 1 minus p will represent the probability that of all of your samples will contain outliers. So what is the probability that that all of your sample will contain outliers? You can compute the probability for a sample to contain an outlier and then multiply this probability for n times. Now the probability for containing an outlier is given by the following stuff. So you have E is the outlier ratio. So your point, so if you random sample a point from your points, you'll have 1 minus E chances that your point will be inlier, and E chances that your point will be an outlier. So if you draw S points, you would have 1 minus E to the power of S, such that your sample, it's a good one, does not contain any outliers. So if you want to compute what is the probability that a sample will contain an outlier, will be 1 minus E to the power of S. So if you want, so this is the probability basically that all your sample will be bad ones, and if P equals 0.9999, you would like this number should be smaller than 1 minus P. Maybe here it would have been better to put smaller than 1 minus P. So in the end, if you do all the computation, you would obtain that if you want to have with probability greater than P, that at least one random sample it's a good one, does not contain any outliers, you should take N to be at least logarithm of 1 minus P over logarithm of this number 1 minus E to the power of S. If you look very closely, this is very similar with what we do for the seminar in the advanced machine lecture class. And here you have a table for which you can compute N as a function of S. This is this column, function of E, which is here, and I think P, and I think P it's 0.99. So if you use S 2, 3, 4, 5, 6, 7, 8, and if you use this E, and if you use P equals 0.999, then for example, if you have 50% of your data consists of inliers and outliers, if you take 17 times 17 lines from your training data, then with probability 99% you will hit a line which is a good one, which doesn't contain any outliers. So in the lab exercise class number 3, when we will try to compute the perspective transformation that will transform a test image to a template image, such that you can align the perspective view of a test of a test sheet with the scan view of a test sheet. We'll employ a ransack algorithm in order to discover a perspective matrix, a perspective transformation that is given by a metric which will have 8 degrees of freedom. So in that case, you will have S equal 8, and depending on the number of inliers or outliers that you discover in the 2 images, then you will need to repeat this process for several times, such that you will get a guarantee with high probability that at one point you will discover a good geometric transformation that will model the perspective transformation that will transform the perspective view of your test sheet in the scan view of your test sheet. Okay, and here you have a plot. If you have p equals 0.9999 and you have s equals 2, and if you have e, it's very large. How many points? How many times n you need to draw samples such that with 99% probability you will always hit a good sample, a line that doesn't contain any outliers points. Okay, now what should be the value of your consensus set size D? So this should match expected inlier ratio, and just one. Okay. Okay. Now this n, so n could take some huge values. For example, here it could take like 1,200, and if you have a great number of outliers, and could grow very fast. So you could determine n on the fly initially. So the basic idea here is that you don't know what is the outer ratio E. So you could pick a case where E equals 0.5. So basically this would mean that 50% of your points will not be on your line, and 50% of your points will fit a line. And you can adapt more and more if you have evidence from the data. So if you would find inliers that are, for example, for a particular model 80%, that then you will update your outlier ratio E equals to 0.2. So for example, in your project, we did at the first exercise lab, we tried to fit some lines to your to some edges discovered by Kenny Edge or just by some thresholded filters, and there you would see that the number of inliers, if you selected just some portion of your images, the numbers of inliers was very large. So there I would say that you have more than 80% points are inliers, and you can easily fit a line using ransack. So now, if you like to adapt your n based on the e, you can do the following stuff. So you start with n equals infinity, and you count samples, and in the beginning you have sample count equals 0, and you repeat the following algorithm while n is greater than the sample count. You choose a sample, you employ your ransack algorithm and count the numbers of inlier points to your model. If the inlier ratio, basically 1 minus e, it's highest so far, then you will set e, you will update e, with it will be equal to 1 minus number of inliers divided by the total number of points, and you will recompute n based on e, such that now you can as before n was equal to infinity, now n it's updated, and as each time you discover more and more inliers, the value of n will decrease, and in the end, at each model you would increase your sample count by 1. At one moment n will be smaller than the sample count, and your algorithm will stop. Okay, let's see some pros and cons for this method. So ransack is very simple and very general. You can apply it to your project, but you have to be very careful how to apply it. So basically, if you want to apply it for your project, you would have to crop some bits of the vertical lines and horizontal lines and try to fit this line only on some crop regions of your image, such that the number of inlier points for each line to be greater than 0.5. Otherwise, if you have a very low ratio of inlier data points for your line, then ransack might not work, or it could work very slow. So usually it should really work good in practice, at least for your project. It's applicable to many different problems. So actually, you can employ it for fitting lines, and also we'll employ it in the last part for fitting a geometric transformation that will model the perspective geometric transformation, as I told you, such that you can transform a test image that contains the test sheet, the test sheet seen in perspective. You can transform it to a canonical view where you have a scan view of your test sheet. Now, what are cons for this method? You could, so at one point, this parameter for the perspective transformation matrix could be quite large. If you have a very small ratio of inlier points, then ransack may not work. And of course, you would need to have at least one model to work well. You would need to sample a model from all possible models from your training data, and this might not be as easy as possible. Okay, so maybe there are some questions until now, because we reached basically the half of our lecture, and maybe we just take a small break of 1-2 minutes, and you put some questions. So did any one of you try to employ Ransack for fitting lines for your project? So what happens when you have points for multiple lines? Does any algorithm works? So what do you mean by multiple lines? So if you have parallel lines, something like that. Okay, so actually it's the case for your project, yeah? Okay, okay. Yeah, so actually, so if you have like a rectangle or like a table, if you look closely at these parameters, so let me go back. So here, initial number of points S. So this should be 2. The distance T should be fine. The sensible parameter it's D. So at one point you have to say that you found a good hypothesis. So you found a line such that number of inliers is that's so the number of inliers it's above this consensus parameter D. So your actually I think that this method would work very well if you know how to set this D. You could return many lines. For parallel lines, I think this will work much better, because for parallel lines, if you fit the threshold T, the distance between any point to your line, such that it's greater than the distance between the parallel lines. So there is no reason that this Ransack method should not work. For tables, you'd have some points that maybe they come from perpendicular lines, and there you could have some problems. But in these cases, you can use more than just the fact that you have edges. You can have the orientation of an edge. So if you add this particular information, then basically you know what pixels to remove from a line, and you'll see that this is the case when using the half transform. The half transform is the method that we're going to discuss next, that will take into account the orientation of pixels, such that each pixel will vote for a line that will follow the direction of the gradient. So my feeling is that for parallel lines will work very well, and for rectangles, if you use the orientation of the edges, also it will work there. So you would have to change a bit how Ransack works there. Okay. 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 Let's move to the half transform. This is another technique that is used for fitting, and in particular here you see how half transform will find a line in this image. So you can see that the green line is localized very well. This is this will be very nice, because I'm pretty sure that you have in OpenCV this half transform implemented. Of course, you have Ransack implemented in OpenCV, And you can try also other models to detect lines in an image for your project. So what is the core stuff for the half transform, and also the ransack method? These are two fitting methods that rely on voting. And the idea for in these voting schemes is that if you have noisy features, these noisy features will vote for some models. And the idea is that if there are noisy features, maybe these models will not accumulate many votes. So these votes will not be consistently. Whereas if you have strong signals, if you have features that lies on some lines, and you have these edges detected, this will vote for hypotheses for models which will be very consistent, and these models will get many votes. And in the end, if you have this status, if you would choose the model which has the highest number of votes, then you will have a method for also that will circumvent the problem of missing data. So we will see this in the next slides. So now, in particular, what does half transform does? It will make basically it will compute. It will represent your lines into another space, in the space of half parameters, and accumulate votes in these half parameters. And each hypothesis basically will be represented by a set of parameters in the half space, and the set of parameters which accumulates the most vote will basically localize best hypothesis in your original space. So, for example, if you want to detect a line in the image space, and let's say that you have some pixel on the line, each pixel will vote for some particular lines, and this line will be chosen such that each line will contain each particular point. And if you have here six votes, though the single line that will have the most votes will be basically the line that will fit almost best all 6 points. So let me present you in detail how this method works. Of course, an application for the line detection and for the half transform is to detect lines for your project. So you can employ half transform to detect the vertical and horizontal lines. And I'm pretty sure that if you understand how this method works, you would also find a good method for finding these lines using half transform. So there is a correspondence between image space and half parameter space, and we will try to find this correspondence. So in the image space, you would parameterize a line based on the equation y equals m0 times 6 plus b0, where m0 is the slope of your line, and b0 is the intercept, is the bias to the origin. And in the half parameter space, you would represent this line as the point m0 b0, that is basically the parameters of your equation in the image space. So a line in an image has this equation with parameters m0 and b0, and this will correspond in the space of the parameters in the half space to the point m0 b0. Now let's see some example. This here I repeat what a parameterization of a line means. So you have the slope m and the intercept b, the bias to the origin O. So m, b are the line parameters, and you represent these parameters. You view these parameters in the half space as a single point. So let's see some examples. So for example, if you have the first line with equation y equals x, so y equals x will mean that if you replace here y equals mx plus b, this means that m equals 1 and b equals 0. A second line is the blue line, which is parallel with the first line. D2 has equation y equal x plus 2. If it's parallel, then it has the same slope. So here you have again m equals 1. And of course that it has a positive bias b equals 2. Another line is D3 that goes also through to origin, and D3 has equation y equals 2 times 6. So here, if y equals 2 times 6, this means that m equals 2 and b equals 0. Okay, and now let's see how these lines will map in the half space. So the first line, if the line y equals 6, you have the parameters m equals 1 and b equals 0. So this will, so for this line will correspond in the half space the point 1, 0, okay, which is here. For the second line, if you have the line y equals x plus 2, so you have the slope 1 and b equals 2. So you have the point, the blue point 1, 2 in the half space. And for the line D3 of equation y equals 2x, you have m equals 2 and b equals 0. So you'd have the point 2, 0. Now, we've seen that for a line in the image space will correspond a point in the half space. And now we will try to answer this question. What does a point x0, y0 in the image space map to in the half space? And let's see some examples here. So for example, if you have the point 1, 1 in the image space, what would correspond to the point 1, 1 in the image space in the half space? So of course, through a point in the image space, there are infinity of lines that will contain this point. And I think I put here a couple of these lines. So for example, the line y equals x satisfies 1 equals 1. So it has the parameters m equals 1 and b equals 0. Also, the line y equals 2 times x minus 1, you'd have that 1 equals 2 times 1 minus 1, which is correct. So this line also contains the point 1, 1, 1, and it has the parameters, the slope m equals 2 and b equals minus 1. And also the line y equals 1 satisfies the requirement that goes through the point 1, 1, 1. This has the slope m equals 1 and b equals minus 1. And also the line y equals minus 6 plus 2 has the parameters m equals minus 1, b equals 2. This line also contains the point 1, 1, 1 because 1 equals minus 1 plus 2 equals 1, which is correct. Now, if I plot these 4 points, point 1, 0 with green, point 2, minus 1 with blue, point 0. Actually, I think there should be 0, 1, yeah. so if y equals 1 is m times x plus b, so here it's a mistake. It's b equals 1. It's b equals 1. I will change this stuff. And point minus 1 b equals to minus 1 2. So if you point all these points, you see that we will obtain 4 points on the line. Yeah. So so the answer is that to the point for a point x0, y0 in the image space, for this point will correspond in the half space a line. So all 4 points, 1 0 2 minus 1 0 minus 1 and minus 2 are on the line b equals minus m plus 1, and this is easily, so this can be derived very easily as if you think about it. So you want to discover all the lines that they contain 0.111. So if all the lines contains 0.11, the single requirement that you have to make is that y0 it's 1, x0 it's 1, and each single line can have every slope m, and so parameters m and b can be whatever you want. So now if you replace this with 1 and this with 1, you will see that each line that contains points x0 equals 1 and y0 equals 1 has to fulfill the requirement that 1 equals m times 1 plus b, and you can see this relationship as the equation of a line in the half space for m and b, and this is basically the equation b equals minus m plus 1. So 1 equals m times 1 plus b will give you m equals minus m plus 1, which is actually the line that contains all these 4 points. Okay. So if we recap a little bit, so each line in the image space will correspond to a point in the half space, and each point in the image space will correspond to a line in the half space. Now our goal is to find parameters in the half space that will localize a line in our image space. Now in the image space, a line is defined based on 2 points. So if you have the 2 points x0 and y0 and x1 and y1, the question is where is the line that contains both x0, y0 and x1, y1 localized in the half space? So now so this line, so the line that goes through these 2 points has the property that goes through x0, y0, and also goes through the point x1, y1. We also know that this point x0, y0 will map in the half space to a line that basically will define the infinity of lines that go through point x0, y0 in the image space. The same will happen to x1, y1. It will also define a line in the half space that defines the infinity of lines that go through this point in the image space. So if you take the intersection of these 2 lines, you would find a point, and that point has the property that goes through that will define a line that will also contain x0, y0, and also point x1, y1. So for x0, so x0, y0 will define the line b equals minus x0 m plus y0. x1, y1 will define the line in the half space b equals minus x1 m plus y1. And if you intersect these points, these two lines, you will find a point that basically will correspond to the lines that will contain all these 2 points x0, y0, and x1, y1. Okay. Okay. Now, so for 2 points, this is easy because you can fit through each 2 points there is just one line that will contain these 2 points. The problem is that in the image space, you'd have some features, basically edges, that they are not collinear. So these points will be misaligned, and of course that when they vote for a particular line in the image in the half space, then you'll have some problems localizing the best pair MB in the parameter space that will identify a line in the image space. So if you add another point here, if these points are quite collinear, then this line will intersect at this point. If this point is not collinear with the other, with the line defined by the other two points, then you will obtain here, instead of just 1 point, you will obtain 3 points. And if you add points on them, and on each point we'll add another line in the half space. And because you have this noise in the image space, in order to find the best line, the best parameter that will define the best line that fits the data in the image space, then you will discretize your half space. Basically, this discretizing your half space means that you will divide the domain for M and the domain of B and in some intervals, and you would obtain some cells in which you will accumulate votes. Now, of course, that now there is the same problem that we had with the least squares. For the vertical lines, you'd have the slope M will be plus minus infinity, which is a big problem. So instead of using the Cartesian coordinates, we will use what is called polar coordinates. So instead of representing a line based on the slope and the intercept with respect to the origin, we will represent a line in polar coordinates. So we'll compute from the origin the perpendicular to our line, and we will denote the distance from the origin to the line with D, and basically D will represent the length the length of this perpendicular. And the second parameter will be the angle that our line will make with the axis OX. So here, this line will be parameterized by this D and this theta. And if you now go to these triangles that are formed here, so if you project the point XY on the OX axis, and if you go to this right angle triangle, if you take cos theta will be equal with this, with x over d. So you'd have d times cos theta equal x. In the same triangle, if you compute sin theta will be y over d. So you'd have d times sin theta equals y. If you multiply the first equation by cos theta and the second equation by sin theta, you would obtain d cos theta square equals x cos theta. And for the second, you would obtain d sin theta square equals y sin theta. If you sum up those two equations, you will obtain, because cos theta square plus sin theta square equals 1, you will obtain d equal x cos theta plus y sin theta. So before, when you had your parametrization with m and b to a point xy would correspond a line, and the line was something with m equals minus was b equals minus 6m plus y. But here, if you go to the polar coordinates, you would have d equals x cos theta plus y sin theta. And this is the equation of a sinusoid curve in the half space. So to a point in the image space, for the point xy will correspond a sinusoid curve in the half space. So I managed to do to write some Python code, and here I plotted the function, the sinusoid curve that corresponds to the point x equals 1 and y equals 1. So for the Cartesian coordinates, for x equals 1, y equals 1, you would have a line in the half space. But if you change the representation, now instead of a line, you would obtain a sinusoid. What is interesting is that all sinusoids will intersect. So if you have two lines, this line could be parallel, but you cannot have sinusoid curves that are parallel. They will always intersect. Okay. Okay. And given this, now you don't have the problem that m was equal plus minus infinity. So now we solve this problem. Now theta, if you think a bit, theta can take values between 0 and 180 degrees. If you go if you surpass this value 180, is basically the same value with so if you have 180 plus theta 1, this will be the same as theta 1, because the orientation of the direction of the line for which a point will vote will be basically the same. Okay, so what is the half transform algorithm in using the theta and d? So I forgot to mention, so theta will go from 0 to 180, and d, so d as it is defined, so this d is the distance between the origin of your image and the point in your image. So this is not actually the point in your image, is the distance from origin to the line. Now you could have a line that, for example, has an angle that is in such a way choose that the perpendicular is out of the image. Now d can have at most value the diagonal of the image. I think, yeah. So there is so the maximum value of d it's the maximum is the diagonal of the image, and theta can take values between 0 and 2 and 2p between 0 and 180 degrees. Now, so you will not have problem in implementation. You can have values that are very large. So the algorithm for implementing the half transform will be the following. So you initialize a matrix H, which is called the accumulator array with all zeros, and for each edge point that is detected as edge by Kenny edge detector or other edge detector, then so for each feature point, for each theta, so you let x, this point x, y, to vote for all possible lines that go that contain this point in the image space. And if you're allowed to vote for all possible for all possible lines, then you look for theta between 0 and 180. So now you have x and y are known. Now you fix theta, so then you'll obtain d. So now you have a possible line that goes that contains point xy is given by d and this theta. So you would increase the value of the bin that is localized by this d and theta coordinates with value 1. And at the end of your algorithm, after you process of all your edge points x, y, you will obtain in the end an accumulator array which will have the maximum value. So the maximum value of a cell in D and theta will localize the line, the most prominent line in the image. So now after this step, after you find values theta and D, where h theta d is a local maximum, so either you take the global maximum and this will identify only one line. If you take a local maximum, you will detect many more lines. So now if you have theta and d are known, you can see now the equation in x and y in the image space. So the unknowns will be x and y, and the variables that you know are d and theta. So we have a demo here. Let's see if this works well. So let's see if I think I have to share now. Let's go back. I want to show you how this demo works. So if I go here and I will share, so new share, I will share you this desktop. Okay. So can you see my browser? Okay. So now, if I will draw a line in the image space, a line in the image space. So a line in the image space basically will be localized by this theta. So theta is here. Theta is 0. So the angle it's 0. Or y 0 should be 90 degrees. Okay. And rho is basically what we call d there. Now, if I have this line here, so if I have this line here, so I managed to draw a line, and you can see that all these points to each point, So each point can be represented by a sinusoid curve, and all the sinusoid curves will meet in this point, and this point will define the theta and d of this line. Let me try again. So let me take this line. So this line. So if you have these edges on these lines, you can see that all the sinusoid curve will meet in a point. Actually, there are two points here. Now, instead of drawing a line, I will take some points. So maybe I start again. So now you remember that to one point in the image space will correspond a sinusoid curve in the half space. So if I put here a point, so you have a sinusoid. Now I put another point and another point here, and another point here, and another point here, and another one. So now you can see that the half transform will work very well, and you will find this point that will localize theta and d that will define your line. Okay, let me draw another one. So let's see what we obtain if I draw a circle. So if I draw a circle, yeah, maybe I draw it again. You will obtain this kind of stuff. Now, if I draw a square, so a square should have like 4 points. Maybe I draw it again. So this is one side, this is another side, and this is another side. So actually, so I should have like four points here, one, and another one. Maybe I draw it once more. Okay. 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 And this and this one. And basically, if you have a square that is axis aligned with that is axis aligned, then you'd have 4 points. These points will have the same theta, and these points will have the same d. Yeah, this will have the same d. So the points which will have the same d or rho, this one and this one are represented. So let me see. So if I take so it will be, so if they have the same, d, I don't know, maybe I draw again. Okay, maybe this one and this one. If I compute the distance rho or d from the origin to the lines, there should be some two distances equal, but I know here doesn't look like. Now let's take a square that is rotated. So if I take this kind of stuff and this kind of stuff, so I'll have 1, 2, 3, or 4 points that will define my my square. Okay. Okay, now move again to the lecture, notes. Let's see if I share. Okay, so now I moved back to the slides. Okay, and okay, okay. So this was the demo that you can play with. Okay, so here you see some visualization of the half transform that basically I also drawn. So for these kind of edges, these kind of points in the image, they will localize quite well. So all the votes basically will accumulate, most of them in just one cell that will localize the D and theta that will define this line in the image space. So for squares, you'd have like 4 vertices, 1, 2, 3, and 4. For circles, you'd have this kind of stuff that I have shown in my demo. And here, so you have also several lines here. Now, if we look closely, so in the left part, you have like a circle and some geometric form. Now, of course, that's to this circle would correspond this part. And now this point should be a point where you have like many lines that intersect. So if you look, so theta should be quite high here, and because of the D it's not so large. So I would say that this point will correspond to the intersection of 3 points, and I would say that is this corner. So if I look through this line will go like this one. If I build the perpendicular to this line is this line, the angle is this one, which is quite high, which is quite large, and the D will be this distance, this one until this one. Okay, so I think this point will correspond to the intersection of the 3 lines, and my bet is that is this corner here. Okay, now if you have a more complicated image, so now we have so we don't see in the left what were the edge points that voted for this line. You have here only the accumulated values for in the parameter space, and you see that you have many peaks which have the same theta, which actually it's fine if they have the same theta. This means that they are parallel. So this line, the green one, and also this one, and this one, and this one, and this one, actually there are 5 lines which more or less are vertical and are parallel. And also you have like horizontal lines like this one, 1 and 2 and 3 and 4 and 5. You also have 5 lines which are parallel. Okay, now what happens when you have noise? So when you have noise, of course, that your features, your edge points will not vote to exactly the same point. So your sinusoid curve will not meet just in one point. So you'll have basically a group of cells which will accumulate votes, and depending on the discretization of your domain, depending on how large you have the the cell, it is possible that all the points could go into one cell, but usually the case is that this vote will spread out into multiple cells. So let's see. So usually, if you have this kind of discretization, so you have small beans, then you see that the peak will get fuzzy and it will be very hard to locate. In this case, would have been a good a good way to fight in these cases is to have beans which have a larger size. Yeah. Okay. And here you have other visualization of the effect of noise. Here you see on the x-axis is plotted the noise noise level, how far your point. So of course, if the noise level increases, this means that your edge points will depart more and more from the line. And in this case, on the y-axis, you see what is the maximum number of votes that will be accumulated in the cell with the maximum of votes. So you'll see that as the noise level will increase, then the maximum number of votes that will be accumulated in a cell will decrease from around 20 to around 5 here. Okay, and of course, if you have random points, then if you have a random points, then you'll have many peaks, but each peak will have just a very small number of votes gathered in a cell. And here you have, so you just take a random points, and on the x-axis you have the number of noise points. So if you have number of noise points that increases, of course, that you have a high probability that this noise point will form some lines. So the probability of getting an increased number of votes in a cell will increase. So here you see, if you take 200 number of noise points in an image, then you have high chances that you'd get around 11 points in a bin. Okay, so maybe we end up with this stuff. So if you have noise, you have a problem with how you discretize your domain. How large or how small are your cell? So if your cell are too large, meaning that your discretization is too coarse, then you will obtain many votes into just one single bucket. But this basically would mean that many different lines will go to the single packet, and they will be identified just as one line. Whereas if you have a too fine discretization, meaning that the area of your cell it's very small, then you would have votes that go to different buckets, and instead of accumulating votes from the same parameters for the same cell, then this will spread out, and you will miss some lines. And one possible solution in this case is either to do incrementation of the neighboring bins. Basically, you can't vote for instead of voting for just one bin, you can vote for neighboring bins, and this can be modeled by smoothing in the end your accumulator array, or you can also try to get rid of irrelevant features, as in this setting each agent will vote for many lines, whereas you can take only you can consider just one vote for the line that corresponds to the gradient of that pixel. And so for example, you can obtain, so instead of allowing theta to go from 0 to 180, for each feature point, which is an edge point in your image, you will allow just a pixel to vote just for one line, is the line that is perpendicular on the edge. And so this is the line that will contain the edge. It's basically it will be basically perpendicular to the direction of the gradient. That means if you vote for the line with the orientation theta, and then you will obtain d equals at x cos theta plus y sin theta, this will be fine, because theta, it will be the angle that your line will make with the axis OX. And so in this setting, instead of allowing a pixel to vote for multiple lines, a pixel will just vote for a single line given by the gradient orientation theta that you have obtained for this pixel. And you can also enhance this algorithm. So here, if you look here, each pixel votes just for one line, but each pixel has one vote, has the same influence, whereas you can make a differentiation between each vote, and consider that pixel which have a higher magnitude should vote, that should have their vote to count more. So here you can change your algorithm such that instead of increasing your accumulating h with just one, to increase your h with the magnitude of the h pixel that is voting. Okay, so let's stop here for the half transform for circles, and we will resume the next lecture with this stuff. If there are questions regarding the half transform for lines. Yes. Yes, so it's okay to apply half transform to obtain lines. It should really work very well. We didn't implement it in the lab session, but if you go to OpenCV, you'd find the function there implemented, and if it should work very well. Should we apply an edge detection before half transform? Of course. So you need either an edge detector or some filter. I think in the first lab, for the first project, we apply a vertical filter and a horizontal filter such that you will get point on edges. So you do have to apply some sort of pre-processing such that you will get points on edges, and then based on these points you can run the half transform such that you get the lines. Okay, cool. Other questions? Okay, so we end up here. Please remember that you have the lab exercise class with Juliana in 5 minutes time. So tomorrow morning I will hold the lab session from 8 to 10. I'll do the same stuff with as Juliana will do starting in 5 minutes. The only problem that I have now is that I didn't install the OpenCV on my laptop. I will try to install it and let's hope that I will manage it. Okay, so see you tomorrow. Bye. Yeah. So maybe I use Colab or maybe maybe I need to install Xcode. I will look over the internet to see what is the bug now with my my Mac, and hopefully tomorrow morning everything will work fine. Okay.